now you understand vector flux. Very important concept. That means you're ready for Gauss's law. Now, I don't want to go on in Gauss's law unless you really understand vector flux. So if you feel still not sure about vector flux, stop this video and go back and watch vector flux again. Okay, I want 80% of you to stop the video and go back. I mean, we have the stats. Okay, I'm going to track it. And if 80% of you don't go back, I'm going to be really annoyed. Okay, so let me stop, go back. Okay, you stayed. You better understand vector flux. Okay, because here we go. This is Gauss's law. Okay, here we go. Gauss's law. Okay, I'm going to give you one more chance. Okay, here we go. The electric field flux you know what that means, right? The electric field flux through a closed surface equals the enclosed charge divided by the permittivity of free space. Gauss's law. This is one of the first that you're going to learn of Maxwell's equations. So extremely important. You must understand it. You must know vector flux first. So there are a couple ways we can write Gauss's law. First is like this. That is what? Yes, that's the electric field vector flux. Must understand that. So that's what it's saying. The electric field flux through a closed surface equals the charge enclosed. I'll call that Q enclosed. So we have to visualize when you see this is a closed surface, you know, a sphere with a charge in it. Over this thing, the permittivity of free space. That's really just a constant of the universe. Just a constant of the universe. It's equal to 8.85 times 10 to the minus 12, and I don't want to mix up the unit on you, Coulomb squared per Newton meter squared, of course. Coulomb squared per Newton meter squared. You don't have to memorize the units of the permittivity of free space, but you have to understand vector flux. Another way we can write it, though, is from what we learned in vector calc. Often you don't see it written this way. Often it's nice to actually show the integral. So often you'll see it written this way. It's the integral, the sum, the total sum of the flux around a closed surface. So this circle means closed surface of, how do you get the flux? It's E dot dA equals Q enclosed over epsilon naught. And when you write it this way, you can see the closed surface on both sides. You can see the integrals over a closed surface and the Q, it's the charge enclosed inside that same surface. So that's the nice way to write it. So this is where we're going to see it a lot, where we would have to do vector calculus, except we'll do lots of nice symmetric cases where we don't really have to. Okay, so you watched it. I hope you understand vector flux. Gauss's law. Let's write it again. You can never get enough. Gauss's law. Let's write it in terms of the flux. The flux through the closed surface will be the charge enclosed over epsilon naught. Gauss's law. So right now, we're just going to think conceptually and visually about Gauss's law. Go through a few problems. Make sure we really believe that Gauss's law is always true, which of course we do, because it would be blasphemy to not believe it's true. So let's start with just a little point charge here, like that. And let's go with a surface that is a nice sphere. It's nice and symmetric around the surface. So Gauss's law says that you're going to get a positive flux. You're going to get a flux because Q enclosed is a positive charge over epsilon naught. So let's think if that's really going to happen. Well, if you go to the surface, there's E. If you go here, there's E. If you go here, there's E. And if you thought about dA, it's always parallel. Okay? So your dAs and your E's are the same all over the surface. So sure enough, that makes sense. You would believe that this would make sense. If Q were negative, what would happen? Well, we know from Coulomb's law the E's would go in, the flux would be negative, everything makes sense. But Gauss's law doesn't require this charge to sit here. What if we had the charge up here? That's going to change all kinds of stuff if the charge is there. If the charge is there. We can think about the vectors again. Right here, it look very much the same, except the field will be bigger. So your E might look like that. But your dA would still be there. That'd be good. Down here, your E might be a little bit smaller because it's farther away. But your dA would still be there. Stranger things would happen at other points. Here, let's see, E would be like that. And your dA, it wouldn't be parallel anymore. But it doesn't really matter. You're going to take their dot product. You're still going to get a positive contribution to the flux. Anywhere you go, actually, you'll get an E field. Most places are not going to be parallel to dA, but they're still going to give a positive dot product. So in this case, all these will add up, and it's believable that it would give you a positive number that's Q enclosed over epsilon naught. And it actually is true. If you did the vector calculus problem and calculated that total flux, you'd get Q enclosed over epsilon naught. So if you think in terms of vector fields, it always works. And what I'm trying to point out here, pointing out that it works, but I want you to believe me that when you don't have symmetry, it also works. It's also true. You just have to believe me that if we did that surface integral in vector calculus, we'd get the right answer. There's another way to look at it, which doesn't require quite as much believing me. I mean, I hope you do. But you can also do it with field lines. Okay? So remember, our field lines was just another way to draw the vector field. So there, we had one go up, one go down. I like to draw 8. Something about drawing 8 of them just feels good to me. And we can put little arrowheads on them to remember which way the field goes. Positive charge, the field goes away. So test charge would fly away. So if you look at this, one way you can think of the vector flux is just how many field lines go through. You can basically just count field lines. What's the total flux of this sphere? It's 8 field lines. Okay? It's not a good unit for vector flux, but it's a way visually just to keep up with it. So the other thing the number of field lines is proportional to is the charge. Remember when we were drawing these diagrams, we said how many field lines do you use if you have 2Q and Q? Well, you put twice as many on 2Q as you do on Q. So the number of field lines is proportional to the charge. So you can now see that if 8 field lines means a charge of Q, then all 8 go out of the sphere, and it's actually anywhere you put it, all 8 go out of the sphere. Right? So this way you can kind of see as I move this charge around, the flux is always going to be the same. It's always going to be 8 field lines coming out. So that might be a more convincing way to look at it. Let's look at a different case where we have our closed surface. Again, let's make it a sphere, and let's put Q outside the surface. Okay? Think about what the vectors would look like. Well, you get a nice big E field here because it's close, but dA is going to stick out because we always put the area vectors out on a closed surface. Out here, you'll have a smaller E field. In that case, it'll be parallel to dA. So this would give you a negative contribution to the flux. This would give you a positive contribution to the flux. And if you add it all up, we'd have to do vector calculus to get it. But you can kind of see you get a lot of positive. You get a small positive flux over a big area. You get a big negative flux over a small area. And guess what you're going to get? You're going to get that the flux E is going to be 0. Okay? If we did the vector calculus, the flux, I promise you, would be 0. And that obeys Gauss's law because there's no charge enclosed. The charge is on the outside. Okay? So that is where you believe me about the vector calculus. Now let's do it with field lines. And maybe you won't have to believe me so much. You don't trust me, it's fine. It's only the 3rd week. I understand. Field lines now. 1, 2, 3, 4, 5, 6, 7, 8, and they all go that way. So before I said you think about vector flux, with field lines, you just count the lines that go out. And that was positive flux. But here, they go in and out. So if we just count field lines for flux, we have 2 in, that's negative 2, and we have 2 out, that's positive 2. So the total flux is 0. And it has to be 0, right? Because all the field lines from this single charge are just going to be straight lines. And if a straight line hits a sphere, then it has to, if it goes in, it has to come out. Because it's a straight line, and the sphere is finite, right? So no matter what you do, you're always going to get 0. No matter where you move this around, it might have 1 line go in, it might have 2 lines. If you get really close, it might have 3 lines go in and out. But you're always going to have the same number go in that come out. So the flux is always going to be 0. So it's always going to match Gauss's law because there's no charge enclosed. Okay? These arguments do not rely on it being a symmetric sphere. You could also do it for a cube. Okay, so here is a 3-dimensional cube. I won't draw the back parts. Let's just imagine we have 2q here, and let's imagine we have minus q here. Those are inside the cube. Okay. We remember how to draw the field lines for that. Oh, well, we had to put more. Say we put 8 lines on the 2q and only 4 lines on the q. Well, one goes down, this goes to here, and this goes to here, and this one goes like that. And we can draw them all and go crazy. And we could we could draw them exact and count the lines going in and out. Okay. If we were to do that, what would we get? Phi e, we would get the right answer. We know from Gauss's law it would be 2q minus q over epsilon naught. It would be q over epsilon naught. If we did all the field lines and counted, I can't draw it accurately, but if we did it, we would actually get the answer q over epsilon naught, which matches Gauss's law. Okay? It's the total in charge enclosed in the volume. You could even do this. What if you put 10q out here? Really large charge there, creates a big field. It's going to really manipulate these lines. Suddenly there's going to be lines, really strong lines going this way, and these are going to warp out and go that way. It's all going to be a big mess with lines everywhere. But if you were to count them, the flux would still be q over epsilon naught, because all Gauss's law cares about is the enclosed charge. It doesn't care about this charge out here. It is true, this charge makes field lines, and it makes a field that penetrates the closed surface, but it goes in and it comes out, and its flux cancels. It doesn't create any flux inside the closed surface because it's not inside, it's on the outside. So this one basically does this. These two basically do this. The details are a mess, but you can always rely on Gauss's law. Gauss's law is always, always true. So I think that clears up everything, except we have one question. Let's see here. Wise guy, what if the charge is right on the surface? Yes, what if the charge is right on the surface? Well, that's appropriate name of that person. So let's say, let's just take one, this sphere. Wise guy is asking, what if there's one literally on the surface? Even if it's a point charge. A point charge is infinitely small. A surface's thickness is infinitely thin. So let's just take the infinitely small limit and say it's sitting right there. So what is the flux now? If we have q sitting right on the edge of the surface, phi e is q over 2 epsilon naught. Even when things are infinitely small, if you put them right on an edge, you still think of half of it on one side and half of it on the other side. So there you get half, q over 2 epsilon naught.